In this video, we'll see a very simple and common way of taking a word and representing it into a vectorial form that we can feed to any machine learning algorithm. This vectorial form is known as the one-hot encoding. So in the previous video, we saw some pre-processing steps for converting words into integer IDs. Now, these integer IDs, they're easy to manipulate. They're numerical, so that's easy for a computer to manipulate and do numerical computations with it. However, we cannot really feed this ID to a machine learning algorithm. I'll discuss a bit more about why that is at the end of this slide. But let me first introduce another representation that uses this word ID and converts it into a vector, which is going to be a better representation to start with if we want to do some machine learning on top of words. So the one-hot encoding, like I said, is just a basic representation for representing a word into a vector. It's using this one-hot encoding approach, which simply corresponds to taking a vector, filling it with zeros, and then putting a 1 only at the position corresponding to the ID of the word. So let's do an example. If we had a vocabulary of size 10, and by that I mean that there are 9 words in the vocabulary plus the out of vocabulary token that we added, which corresponds to the 10th ID. So then the one-hot vector for the one-hot encoding vector for a word ID which is 4 would be the following. It would be a vector where everything is 0 except the element at the position 4. So 1, 2, 3, 4. We see we have a 1 here. I'm going to note that E of W, so W is 4, and E of 4 is going to be this huge vector with just a single 1 in it at the position 4. What's nice with the one-hot encoding or one-hot vector is that it actually makes no assumption about the similarity of the words. Specifically, if we're looking at the squared Euclidean distance between the representation of a word W and a word W prime, so if you take the difference and then look at the Euclidean norm of that difference, it's going to be 0 if W and W prime are the same, that is, they correspond exactly to the same word. And otherwise, by simple calculation, you'll see that we get a distance of 2 if W is not W prime, so if they actually correspond to different words in the vocabulary. So in other words, all words are equally different under that representation. So that's a much more natural representation to start with. We're not making any assumption about which words are more similar to which other words. We're going to leave that to a subsequent learning algorithm to learn this. So that's better than actually feeding the integer value W, because otherwise if we had a word which has the ID 4 and then we had a word W prime which has the ID 5 and then another word which has the ID, so W prime prime, say 10,000. So it just happened to be lower down the list in the vocabulary than this word. Then if we look at these distance between 4 and 5, that's much smaller than between 4 and 10,000 based on the integer value. However, it might be that in my vocabulary, well, 4 is actually dog, E is maybe jump, and then the W prime prime might be cat. And we might argue that dog and cat are actually closer than jump and dog, for instance. And this is only because we didn't put any thought into the ordering of the words. And also there's no really simple way of putting each word on a single line and putting them in a position which is actually meaningful. So that's why we can't really use the ID for the words. They're usually not going to represent a meaningful similarity between the words. So we're going to instead start with the one-hot encoding representation, which is actually encodes no particular, makes no assumption about word similarities, and then we'll leave it to the learning algorithm to try to learn which words are more similar than others. Now, still there is a big problem with the one-hot representation or one-hot vector or encoding, and it's that it's very, very high dimensional. So the dimensionality of a one-hot vector is the size of the vocabulary. And like we've mentioned before, typical vocabulary sizes can vary between 10,000 to a few 100,000. And that's just for one word. Now imagine we had a sequence of 10 words, a window in some text that contained 10 words. And we wanted to encode the position of these different words, so we want to concatenate these one-hot vectors, so that gives us a total vector of length 1 million if we had 100,000 for the vocabulary size. So that's much bigger than most problems that we usually facing with neural networks or most machine learning problems. So the consequence of having a very high dimensional input is first we'll be vulnerable to overfitting. If we have millions of inputs, then it means that, so the size of our input is in the millions, then we're probably going to have in the millions number of parameters in our, say, neural network or any other learning algorithm, really. So if we have millions of parameters, it means that we need a lot of data to estimate well these parameters without overfitting. The other problem and consequence is that this can imply some computationally expensive computations that we'll have to do when we manipulate these vectors. Specifically because not all calculations or computations can be sparsified. So the one-hot vector can be sparsely encoded, so into a sparse data structure. And sparse vectors multiplied by matrices, for instance, can be done fairly efficiently using a sparse implementation. However, there are other operations. So for instance, the reconstruction in an autoencoder, what we'd want to, for instance, reconstruct this whole window of words, that cannot be sparsified easily and trivially. If we did an autoencoder, we would actually need to reconstruct each of the element in this vector of a million. And so those are the two consequences of using this basic one-hot representation, and these are issues that we'll try to tackle in the different algorithms that we'll see in different ideas we'll see in the following videos.